Quick audience poll. The brave few of you that have made into this deep dive. We're going to get into some nitty-gritty about processor execution, et cetera, to analyze Meltdown and Spectre. But the poll, show of hands, who has heard of Meltdown and Spectre before? Most of you. Keep your hand up if you understand the exploits, how they can be used to attack another process or another guest VM. Okay. Keep your hand up if you understand the fixes and how the Linux kernel and VMs are patched. Okay, we're looking at 3 or 4. Okay, and then if you don't know that, you might not know how it affects Apache Spark performance. And my laptop has decided to go to sleep. Anyways, we'll keep moving then. Okay, so in early January, when Meltdown and Spectre were disclosed to the public, the ecosystem scrambled to patch our software and hardware. And at Databricks, we published a blog post, because we're data-driven and we care about our performance, about the effects of these patches on our Spark workloads. And so in early January, we published this terrible graph. There's a few reasons why it's terrible, not to mention why it's not even telling you what the lines are. They are different configurations of the Databricks runtime run on different AWS instances. But the point to be made is that on January 3rd, there was a 3 to 5% uptick in the geometric mean of query runtimes for some configurations. And so the goal of the talk today is to understand where that 3 to 5% comes from. To do that, we will look at some TPCDS benchmarks that I ran on a local Linux box I have sitting around. It's a 2012 Ivy Bridge for those that care. So it's not the best machine, but it was available, and I could disconnect it from the internet. And I'll do a deep dive into those queries to figure out what the system is doing when it's running the queries, and couple that with explaining the Meltdown and Spectre exploits and the patches. All right, so if you're not familiar with TPCDS, it's a set of queries and tables that we use to benchmark Spark. I ran a bunch of them on the machine. Here's one that's somewhat interesting in terms of results. It joins 4 or 5 tables together that combine up to 2 to 3 gigabytes of data. And it's really just trying to figure out something about customers in Tennessee. Here's the Spark plan. It is 8 stages and fairly complex. And voila, here's the documented runtimes. Just blanket, here's what happened when you add the Meltdown and Spectre patches. There's a bunch of letters on the bottom. I won't explain those now, but I'll get to them. But the point here is that we can see a 2 to 5% increase in the geometric mean of the runtime for these queries on this one particular node I was running. Now, it's a matter of hundreds of milliseconds. It's not a whole lot, but on a 13-second query, that is 2 to 4%. And so I asked myself, what is going on here? Why, when I add these patches, is my query taking longer? And so the first thing I thought to do was to figure out what the CPU is doing. And it turns out, as we add more of the fixes, more of our CPU time is going into the system, spent in the kernel. And I used mpstat to monitor the query as I ran it to figure out what was going on. Now, how do you get into the kernel? Well, you make system calls. So I went and analyzed the most popular system calls for my particular query and looked to see their average runtime or average time spent in that system call based on the configuration. Now, the scale here on the left is in microseconds. Not a whole lot of time, but when you call these system calls hundreds of thousands of times over a 13-second query, this can add up to hundreds of milliseconds, the exact difference we are seeing in our query performance when we had the patches enabled. All right, so that's sort of where we're going. More time spent in system calls. Now the question is, why? All right, before we dive into Meltdown and Spectre, we need a little bit of education so we can understand the exploits themselves. And so we'll talk about out-of-order execution and side channel attacks. But first, look at in-order execution. So I wrote a really dumb program. It adds 4 numbers together and does it in 3 steps. And in order execution, you have to go line by line, and you couldn't execute the second line in purple until the first line finishes. So this is our execution pipeline, and you can see it's quite slow. But the astute among you might realize that C and D, the addition of those 2, does not depend on the result of A and B. So with out-of-order execution, we can actually parallelize some of this work. And it looks like this. We'll overlap the first line and the second line, and then do as much as we can of the third line until the results from the first 2 are ready, and we can do that final add. So this is key point number 1 for the attacks, out-of-order execution. Key point number 2 is side channel attacks. A side channel attack attacks the shared cache between all processors, the lowest level shared cache. And on most systems, that would be your L2 cache. And what it does is it will flush the cache entirely. So on the far left, you see the cache has data in it. The attack will flush it. So the entire L2 cache is invalid, which means, okay, so back up, L2 cache. People with me? What it does? No. Yes? Okay, great. So it prevents you from having to go to RAM or the page tables to do a virtual to physical memory lookup. So we save some time if we read from the cache. And so after the flush, the attack happens, and the attack will touch one of the cache entries. And once we finish the attack, we can go and scan through memory, reading, and essentially looking at the cache performance. And with a fine-grained timer, we can say, how long did it take to do each read? And the read that took the shortest amount of time is the cache entry that the attack modified. And so, taking from the Meltdown paper itself, this is their chart for a side channel attack. You can see that there's a significant drop-off in one of the readings, which would tell me that cache entry for page 90 was affected by the attack. So this is how we're going to snoop the data. Out-of-order execution is how we're going to get the side channel attack to perform. All right, Meltdown. Attack number 1. This is our code, fairly simple. This is all the attacker needs to run in their process to read kernel memory, which we thought was sacred and protected from user mode. It turns out it's not. So here's our complicated pseudo-execution pipeline for that bit of code, somewhat color-coded. And so when we're doing this read of the kernel address, we will actually proactively go look and try to do the next line, which we've decoupled into a multiply and a read of an array. But we will find out that the read for the kernel address will take some time, and so we've done this extra work. And when it finishes, when the kernel actually when the processor actually hands back that kernel memory, a race is on. Eventually, the top line in blue, that instruction will get retired. But if the out-of-order execution of the subsequent instructions are able to execute and get to this side channel attack on the bottom right, before the retire and the permissions check, we will actually have affected the cache. So that permissions check is what is actually checking to say, this is a kernel address, you don't have permission to read it, but we do it after we've already read the value into a location that can be snooped by future instructions. Mind blown. Intel, this was not what we thought was going on, and it has opened us up to a bunch of attacks. And so this is Meltdown in about 30 seconds. It gives us the side channel attack, which we can look again to say, okay, the attacker flushed the cache, the attack happened, it influenced the cache at offset 2, and so when we go back and read, we see that offset 2 took less time, which really means that when we did kernel byte times 4096, that kernel byte was 2. So we actually learned what was read out of the kernel via the L2 cache. All right, so how do we fix it? It's called kernel page table isolation. On the left-hand side is the old world that we used to know and used to love. Each process only had one set of page tables. It would map both user mode and kernel mode, and we thought that a process executing in user mode could not touch the upper half of these page tables. Meltdown proves it can. And so the solution, KPTI, is to have 2 page tables per process. One for the kernel, which looks largely identical to the prior version, and a new set of page tables for user mode in which the kernel memory is not mapped. So as a result, when the Meltdown code does that read of the kernel address in our execution pipeline, we get red lines because the read did not succeed. There was no memory there. It did a page table walk. It found nothing. It could not return anything. There's no side channel attack. We're safe. Cool. Well, let's see. You're going to say, Chris, well, there's some cost to maintaining 2 page tables per process. Yes, there is. One's for user, one's for kernel mode. So as we make system calls, we need to swap between them. Now, this is a write to the control register 3, CR3 on Intel chips. And a write to CR3 will actually clear the TLB, the translation look-aside buffer, which is what saves us from doing page table walks. And actually saves quite a bit of time, tens of nanoseconds, which add up. And so, when we look at the TLB before KPTI in another dumb little program that prints a user mode address, then makes a system call, which will do some sort of kernel read. This is in the old world, where we see the first time we go to try to print the user address, we get a TLB miss. So we have to do a page table walk. Then we'll call into the kernel, and we will do another TLB miss because we've never touched the kernel time address. And so we'll do a TLB walk, but fill in the TLB. And when we circle back into user mode the next time, we'll actually get a TLB hit and be able to access the user address, saving a bunch of time. With KPTI, this is what happens. We get no TLB hits because between each of these phases, as we go into the kernel and back to user mode, we are clearing the TLB. So we're losing performance because we are always having to go walk the page tables. All right, finally back to some data. So this is what the TLB misses look like when I'm running my Q1 query. On the left, we have my system configured with none of the patches. And on the right, we have the third from the left, we have the KPTI patch enabled. And you can see there's almost a 50% increase in the number of TLB misses while running this query. That's not great because as each TLB miss can add nanoseconds, well, if we're doing millions of TLB misses per query, those add up to milliseconds, which is the difference we see in our total runtime. Now, there's 2 other bars here that I've included. And some of you who are aware of what's going on might have heard of PCIDs. They are processor context IDs, and they save us some, as you can see, the headache of doing these context swaps in and out of user and kernel mode. And so we'll explain PCIDs here. Back to our example. A PCID is tied to the page tables that are currently running in the processor. And so when you get a TLB miss and load a value into the TLB, you tag it with an ID tied to the page tables. And so then when you do a TLB read, you only get a TLB hit if your current page table's ID matches the ID in the entry. So again, the first read is a TLB miss, second read, TLB miss, and as we swap back to user mode, we actually don't clear the TLB because we have this PCID, And when we do print user address, we'll actually hit the TLB and move on. So it saves us some performance. It's not perfect because there still is the overhead of swapping the CR3 register, which is not necessarily free. All right, and then this is sort of the runtime with just these Meltdown patches, and it's about 2 to 4% when we add the KPTI plus PCID. All right. It's Meltdown. How are we feeling? Got some thumbs up. All right, Spectre. There are 2 versions of Spectre. The first one is known as bounds check bypass. And unfortunately, fair warning, I do not have any performance results for this one because the patches are enabled by default in the Linux kernel and you cannot turn them off. Well, there are only 14 occurrences of the patch in the kernel, so there's really negligible performance impact. And Red Hat actually did an analysis on this patch and said, we don't care, that doesn't do much because there's only 14 occurrences, and we didn't notice any change. But for completeness, we'll explain it. So another short program, just that accesses an array, but makes sure, as you might want to, that the index that accesses the array is within the bounds of the array. And this seems like very logical code, but because of a special type of out-of-order execution known as speculative execution, the processor will actually make a guess as to what to do next when it encounters that if statement. Otherwise, it would have to wait to see if the if is true or false to know should it do val equals array index or whatever comes after the if. And in order to not lose that time, we make a guess, and thus our execution pipeline looks like this. So as we start decoding the if statement, we look in a cache, a branch predictor cache, to say, what was index versus size last time I got here? Was index less? And if the answer is yes, I will start speculatively executing the purple instructions. And as you can see, if you can follow along here, this results in a side channel attack. What we've done is we've taken an opportunity with this array to access beyond the bounds of it. And so what an attacker can do is train the cache with good values. So here, I'm going to train this cache with an index of 5, and given that size is 10, the program will think that when I encounter this if block, I should move into the if block speculatively because of the last time I ran this, index was valid. Fine. You've primed your cache and it says, yes, you should go down this path and do a side channel attack. Of course, the attacker is going to do that, prime your cache, and then give you a really big value, at which point it blows off the end of your array, reads whatever value it wants to out of memory, and uses that to touch another array, which then they will analyze via flush and reload with a side channel attack to figure out the value of val. Pretty nasty stuff. So this fix that appears in the Linux kernel 14 times is really just a one-liner, OSB. And OSB is an alias for the lfence instruction. This is an Intel instruction that pauses speculative execution until all prior functions complete, or all prior instructions complete, and does not start any new speculation until after the lfence barrier completes. And so what does this do to our execution pipeline? With that OSB, we will speculatively execute the OSB, even if the attacker has primed the cache, and we will hit that lfence, which prevents the read from the array from starting until after it finishes. So in this sense, we're safe. And if index is in fact bigger than size, none of this stuff on the right side will actually happen. The processor will roll back and will move on without being susceptible to a side channel attack. All right, again, no fun graphs for that one. Spectre V2, branch target injection. This is the fun one because it makes a guest VM susceptible to an attack from another guest VM. And this is what really needs to be patched if you're running cloud workloads. All right, and it has to do with indirect branches, and so function pointers are an example of that. So I have a dummy routine that takes in a function and some arguments, it's going to call it. It doesn't know a priori what that function is going to be, and so it'll actually need to do some speculative execution via branch prediction to not waste time while it's reading that function's actual value. And so, again, here's an execution pipeline where the first line is attempting to read the function's true value from memory, but to not waste time, the processor will speculatively execute to say, well, what was func last time? Let me go execute that. I don't care what it was, let's just do it. A bit cavalier. And so it'll do it, and if it turns out that it matched what the current func value is, great, we've already done the work. If they don't match, we toss the work, we go back up to the blue, call a real function, and move on. Of course, this also can be exploited. And so on the left, say we have our malicious attacking guest VM, and it is going to train some function that it's made up. It's pseudo code that looks similar to the victim's VM's code with this attack widget. And now this attack widget, what does it look like? Well, it's array accesses such that you can do a side channel attack. It all looks sort of like the other exploits we've seen before, but this time it's an indirect function call. And so our attacking VM will train our branch predictor cache down in purple to say, when you ask me to figure out what func is, well, I'm going to tell you it's my attack widget. So thus, when the victim VM goes to execute its code, trying to call innocent, well, it has to go load innocent from memory, and in the meantime, it'll actually execute attack widget, which might snoop the innocent VM's memory and return those values back to the attacking VM. If you followed that, you're really with me. There's a lot going on, and I only have 7 more minutes. All right, so how do we fix this one? The answer from Intel was to update the microcode to flush the branch predictors more often, to flush these caches on kernel or user mode to kernel transitions and from guest VM to guest VM transitions. And that really slows us down. And so here's the answer. We will, between a transition from the attacking VM to the innocent VM, these Intel microcode operations will clear this purple cache, and thus, when the victim VM goes to try to run the innocent function, it will do nothing. It'll wait for innocent to be loaded out of memory and actually run the innocent function. And again, here it is, cache miss, we won't do anything bad. Okay, so here's the graph. These are branch misses. So when we clear the branch predictor caches more often, logically, we will get more misses. And here it shows up in our Spark query. And this, again, is like a 25% increase in cache misses. Each cache miss has to wait. Add that up by hundreds of thousands, you get microseconds or milliseconds worth of time added onto your query, which you can see here, which is like a 5 to 8% jump when just looking at these patches. Okay, for those that are really attuned to how in the Meltdown and Spectre world, you're going to ask me about repo lines, or repo-leans, I don't know how to say it. This is Google's solution for Spectre V2. It doesn't require clearing the branch predictor caches in all cases. Some cases it still does. And so some assembly required. So you're brave to be here. The original on the left was a simple one-line assembly instruction to jump to some unknown location stored in a register. What repo-lean does is substitute that instruction for this batch of instructions in blue. And so what it will first do is a direct call to a known location called setup target. Direct calls cannot be influenced by the branch predictor cache, so we're safe. And what it'll actually do on the call instruction is push the return address onto the stack and into another cache called the return stack buffer. So we've got this return address, which is speculative loop, our next instruction line, and that's stored in 2 locations, and we'll actually jump to setup target. The first thing setup target does is modify the stack value, because the stack value is the source of truth when we actually do the return. And so it'll move RAX onto the stack and then carry on to the return. Of course, the return needs to go read the true value of RAX out of memory to be able to jump there. So in the meantime, it's going to speculatively execute based on the return stack buffer. What did we put there? We put in speculative loop. So it's going to sit here forever, unaffected by the branch predictor cache, in loop, waiting for RAX to be read out of memory. When RAX is read out of memory, we will actually return to the RAX location, effectively executing the same jump we had before, just with an infinite loop in the meantime. That doesn't sound so great. We got no branch predicting anymore. We used to have some. We would occasionally clear the caches. We could benefit from it. Now we have none. Google came out and said this had no performance impact. I don't know. It's sort of up in the air. This may be why, because if you've ever looked at Linux kernel, there are some if statements here and there that say if likely or if unlikely. So if you have some sort of branch or function call and you know that more often than not it's going to go to a known location, you can instrument your assembly to look like this, to say compare it against that known target. If it is that known target, let's jump directly there, unaffected by branch predictor cache. But if it's not, let's enter this infinite loop of retpoline. And so maybe that's why in most cases they aren't seeing any performance impact, is because this is the common case, is that there's typically a known target. You could think of like a file handle that has a function table, and when you call this system call, more often than not, it calls this function out of the file handle's function table. Seems logical. So what's the runtime look like? Well, it's noticeable. It's not so bad, though. So there's something going on there, but so Google may not be completely right, but they're not way off. It's not terrible. And again, you can kind of look at the CPU utilization to see that we are spending a little bit more time in the kernel when we have retpoline on. And here is actually an example that not all system calls are equal with retpoline, which may be that, in this case, close is benefiting from that known target, but open and read are not. They have to go sit in the infinite loop. All right, so with 1 minute and 45 left, here's the lesson of today. There's all that, security exploits, you need to patch your software, great. But when it comes to Spark and things like this, these kernel patches, it's really a tale of 2 queries. Not all queries are created equal. Up until now, I've been talking about Q1 out of TPCDS. Now I'll introduce you to SSMax. It reads from one table, and in my case, that table stored about 13 gigabytes of memory, but the results were actually pretty boring. It wasn't affected by the patches, and the question is why? Well, it doesn't call into the kernel as much. This SSMax query will read its data, churn on it, trying to find the max value on each worker thread on this single node, and do the math and coalesce and exit. It's not managing all these different tables, calling into the kernel to do opens and closes. It's fairly simple, and it's doing like a 1/6 amount the work in terms of system calls. Thus, it gets higher throughput, and it's unaffected by the patches. All right. Cool. Thank you. Meltdown and Spectre in 30 minutes. Questions? Or I'll be around. Yeah.
Did you try to aggregate the kernel code, the kernel calls to be together to mitigate the impact?
So like which system calls are more impacted by it than others? I'm not sure I understand the question.
Did you do any changes to the code to mitigate the performance effect?
No. So I took, I have a slide here somewhere about my setup. There. So I took Ubuntu 16.04, 64-bit server image, load it on my Ivy Bridge desktop, and then really it's just kernel command line parameters. And they, I think, are maybe on one of these pages. Yeah, just to disable them, enable them. So like the microcode stuff from Intel, that when you can actually write into proc sys kernel IBRS enable, and that will call into the system to enable the microcode in real time. Everything else has to be a command line switch that you do at boot up. Oh, I did no changes to Spark. Is that your question? Yeah, no changes to Spark. Yeah. So the question is, train and attack, and I talked about how you could put it into the manage the cache and how would an attacker actually do this. Is that your question? Okay, so yeah, it's complex. And so this is a simple cache which only has one cache entry, right? And maybe your question is, well, your cache doesn't have one entry, it's got 1,000 entries or so. And so what you need to do is, because you can't run the victim code, you need to make a piece of code that models its behavior in terms of cache line access. So I want on the left, the attacking call func to have the same cache alias as my victim's call func. And so it's finding what that alias is no easy feat, and I wasn't going to attempt to explain that up here, but we can talk after. Yeah.
So that SS query, like, does it do the same thing as the original TPS-DS query?
No, so I've got its, so this is its Spark plan.
It's not a rewrite of that same query.
Of the Q1. No, they're completely different queries. So they actually look at, this SS query looks at the stores sales table out of the TPCS data, and the one on the left looks at 5 different other tables.
So is there any way you can take an existing Spark query and rewrite it to mitigate some of these effects you're talking about?
Interesting. Yeah, I mean, it depends on the number of system calls it's really making to the kernel, so you'd have to do an analysis, and the point here is that, like, if you want to know how it's affecting your queries, you really have to go look at your queries. And so as far as a rewrite is concerned, have to do some deep dive to say, okay, here are the system calls I'm making, here, and if you're in a cloud environment, here are the network transactions I'm making. Can I reduce those in any way? And that's one way to go about looking at it.